this lecture I would like to talk about surface integrals. This topic is closely connected to triple and double integrals, since we are computing surfaces. In this case, the difference with the double integrals, if you want, is that double integrals allow you to calculate surfaces that are plane surfaces. What do I mean by that? Well, double integrals are used to evaluate the area enclosed by a curve. So this is a surface, but it's a surface belonging to a plane. Whereas in surface integrals in general, we can have a function and we want to evaluate the surface of some part of that function, and that surface doesn't lie on a plane in general. So this is the difference. Surface integrals can also be converted to double integrals, and we will see that. So there is a connection, but surface integrals are more general. Let's start by considering this function right here. This is the function, for instance, f of xy, but let's be more general. In general, if you want to describe a point in space, this point P has three components, x, y, z. But if you want to describe a point on a surface, we need two parameters. If you want to describe a point on a curve, we need one parameter. But on a surface, we need two parameters. For instance, let's take this surface. We may need a parameter in this direction and another one in this other direction, because we have a two-dimensional object. So we need two parameters, and we will see that in greater detail. All in all, x, the coordinate x of the point, can be written in terms of these parameters u and v. So can y and z, y of u, v, and then we have z as a function of u and v. All in all, we have a vector characterizing our point. The vector x is characterized by the coordinates x, y, and z, and these are functions of u and v. Let's take a very small element of the surface. So let's take an element in here, but I will magnify the element here. This is an infinitesimal element ds of our surface. This is the point x, y, z. So it is a function of u and v. X of u, v, y is a function of u, v, and z is a function of u and v. And we know that in general the area, the S, is the magnitude of the cross product between these two vectors. I will call these two vectors v1 and v2. So it is the cross product between v1 and v2, and then we take the magnitude of that. So that's the S. Can we express v1 and v2 in terms of things that we know? The answer is yes. Because in general, when we have this surface, what is this vector right here? Remember, we have two parameters. One is along the direction of u, and the other one is along the direction of v. So this is the direction of v, and this is the direction of u. They are two independent parameters. This vector here is characterized by the change in x with respect to u times du. This is the change of the vector u along this direction. And what about v2? So this is v1. v2 is just the change in the vector x along the direction v. So it's dx over dv. So you can just think of v1 as the difference of two vectors. This is v1. This is the vector x. Whereas this vector right here is just x plus dx over du. This small change is the change that we want, because if we take the difference between this vector and this vector, we get this one. And the difference between this one and this one gives us this vector right here, dx over du. So we take the cross product between these two vectors, and that's pretty easy. So ds equal to magnitude of dx over du cross dx over dv. And then we have a du dv that we can factor out of the magnitude, because this is an area and is always positive. So in general, if you want to integrate the surface, we need to sum all these contributions right here. So we have to integrate, and this integral is actually a double integral, as you can see, a double integral of the parameters u and v. And we will do some exercises. In general, when we have a surface, it is very important to give the surface an orientation. And the orientation is characterized by the unit vector, which is pointing outwards of the surface. If we have a surface like this one, I will represent it in here again, we can also draw a unit vector going outside of the surface. This direction is important in some problems, especially in physics, which I will not discuss in here. This will be very important also in the case of a theorem, which is the Gauss-Green theorem, and we will see that theorem in further lectures. If we take the cross product between this vector and this vector by the right-hand rule, which tells me that if I move from the first vector to the second one in the cross product, the thumb gives me the direction of the unit vector. This is important. Instead of considering the magnitude of this cross product, if I just remove the magnitude, the result is just the unit normal to the surface times the surface itself. So n ds, when n is the unit normal coming outside of the surface, is equal to dx over du cross dx over dv. These are brackets, they're not straight bars to indicate that we have to take the magnitude of the vector inside, times du dv. So in general, if we want to calculate the unit normal to a surface, we can just consider this thing here divided by ds, dx over du cross dx over dv times du dv divided by ds. But we know what ds is, right? ds is just this expression, so we can just divide by magnitude of dx over du cross dx over dv du dv. So these two cancel. And this is the expression for the normal to a surface which we will use. We will elaborate on this a little bit further, but for this lecture, this is it.